Energy has a quality to it, which we're gonna talk about much later in this course. There is a high quality energy, such as the energy of the gasoline in your car, or even higher quality still would be the electrical energy. High quality means that you can easily convert a large fraction of that energy into the mechanical form, such as turning a turbine and moving a car, doing something that you want to do. Yeah. So we have to come back and talk about these extra elements that's associated with energy to talk about how useful the various forms of energy are. It's also critical when you're thinking about the environmental issue as you leave this course and start applying this to recognize that the planet Earth is not an isolated system. It's not isolated system. The total energy available to a human being is not a fixed number because we have energy flowing from the sun. There is a power from the sun, energy per second coming in, and it's a lot. If you look at the total solar energy flux on the planet Earth, there is a lot of joules coming in every second, every square meter on the planet Earth. There is a reasonable amount, and it's partly a question of the efficiency. Can we use that, and how much of it can we convert into the form that we want to convert it into? It's pretty easy to turn it into the thermal energy. It's very difficult to convert it into the energy of motion, which is what we tend to want in our society. At this point, I'd like to leave the energy story for a little while. We will be using the energy concept throughout the rest of the course, but I'd like to step back and try to take the broad view of what we covered so far. So, summarize some of the key ideas, the great ideas of the classical physics that we look at so far, and try to think a little bit about where we might head with this. I would argue that we've done in this first half of the course is try to look at the rule of the game, try to look at the rule of the game, the rule of the classical physics, and from those rules we're gonna be able to start applying them in practical situation we've already done or that talked about how you might do that in the specific instances. And indeed, I could list the fundamental ideas that we've talked about. So we started off with the microscopic ideas. We were looking at the little point-like particle, and we talked in a very strictly Newtonian fashion about how you understand the motion of the object. That's really what Newton was trying to do. We began with kinematics, pure description. You have an object, you measure where it is, you measure how its position is changing over time. We talked about the reference frames, and you can choose to look at the object from any vantage point you like, as long as that is an internal vantage point. Wow. Sorry. So, I made a mistake. So you can choose to look at the object from any vantage point you like, as long as that is an inertial vantage point. As long as Newton's first law holds, then you are free to describe the kinematics and understand what's going on in this way. We've been pretty careful about words, so we've been defining the velocity and acceleration. And then we moved to the Newton's dynamical laws, his explanatory laws. Dynamics is the explanation of kinematics. So Newton's law, and in particular F equal ma, is allow us to understand the causes of motion. Why does something change in its motion? Because you apply a force to it. Pushes and pulls are the centerpiece. You are still focusing on the micro in this worldview. Then we took a little step back and we started thinking about momentum. Momentum is now not about interactions. It's about the particle itself. You have some momentum. It's a property that you can measure. And when you start thinking about property, and it's a flow and transfer, you tend to step back. You tend to think more about Newton's second law and third law together, that the force of A on B is equal and opposite to the force of B on A, so that you can look at the system as a system as a whole and stop worrying about those internal forces. So this is going macro and moving out to the slightly more abstract concept. So you cannot touch or feel momentum like you can touch or feel a force, but on the other hand, it allows you to deal with progressively more complex systems. Newton's laws, of course, defined and explained this momentum story. Momentum was not new idea of physics. It was just a re-description or re-thinking of the Newton's laws, and we started thinking about conservation. Conservation of the momentum is a principle. It tells us something useful about complex system again, so that we don't have to worry about all of the details. If there is an explosion and crashes going on inside, we can use this principle of the physics derived from Newton's law, but thought about in terms of the momentum to simplify our life. Ooh. Oh. So, momentum conservation also led us to think about systems as simply as possible, so that as we moved to the complexity, we realized that yes, complex systems are real. Complex systems are real, and in the practical world, you have to worry about them. However, you can focus your attention on the center of mass, and the center of mass now allow you to think about arbitrary system in terms of its motion as a simple particle. Wow. So it's all about the logical game, isn't it? Yeah? I think so, at least. So that's nice. It's justifying our think simple approach to physics, and yet simultaneously allowing us to move to more macroscopic and complex phenomena. The last stage of this was the concept of the work, and then the concept of and the conservation of energy. The energy is new ideas. It's a transfer of work. Work was defined in terms of force and distance. So we went back to our old Newtonian ideas to define this concept of energy. Now we are beginning to see that energy itself is a lovely way of explaining things. Yes, of course. Energy. Energy flows. Objects go from high to low because they want to convert their gravitational potential energy into the kinetic energy. It's just another way of thinking about why things happen, and it's nice and easy because it's just a number. Energy is the easiest mathematically of everything we've talked about so far, which is one of the reasons why engineers love it. Every scientist loves to think about energy. When we began this course, I said we were thinking about space and time. And indeed, that's really where we began with kinematics. Space is a position and time is how things evolve. We thought about space and time, matter and energy, and force and motion. Matter, well, we've been talking about mass and inertia, the property of the matter. Matter and energy and force and motion, all of these at the beginning of this course may have looked like disconnected, separate ideas. And one of the big ideas that I'd like to emphasize today is that really it's all about very small number of things. It really boils down to Newton's laws of motion. Yes. Yes, it's nice to think about the things in terms of the mass times velocity in some circumstances, or half mass times velocity square in another. We are just combining these basic ideas in different ways. At this point, we were well equipped. We are well equipped. We can really tackle arbitrary problems, and just look around the world and think about the things that you might be interested in, the question that you might have. The questions could be, this question could go into other fields such as biology, chemistry, or geophysics, but there is plenty more physics to be tackled. There are other forces. There is other forces of the nature, such as electricity and magnetism. There is heat, and there is thermal properties of the materials when they expand when you heat them, and how all of this work. You could think about light, optics, and sound, and of course, as the course goes on, we are going to tackling all of these things, and we are going to be trying to move in the systematic way from our building blocks. Sure, we always going to be thinking about force and motion and energy, and then when we talk about a new force such as electricity, well, we'll connect it to forces that we've already talked about, such as gravity. Ooh. Ooh. It's just another one, and the gravity is just another, and once we understand the nature of the electrical force, then Newton's law takes over, and conservation laws, and we can understand what's going on, and how to make sense of the world that we live in. I'd like to also take a kind of philosophical step back. Those were the topics that we've covered. But what's the idea of classical physics? What's the idea of the classical physics? Classical physics is a viewpoint. It's built on the philosophy. So there is a bunch of elements to this philosophy, and I'm trying to articulate them as we go along. Classical physics treats the world as something real. The world is outside of us, and you can abstract away from your own personal experiences and think about the object and the forces, and you don't need to think about our interactions to our measurements. There are things going on out there that we are measuring and making sense of it. That's a part of the classical physics worldview, which modern physics might disagree with to a certain extent. In the quantum mechanics, there are circumstances where what happens depends on what you choose to measure. Wow. I'm not arguing that classical physics is the way the world is. I'm just describing this very, very productive way of thinking about the world. So, it's a deterministic and mechanical worldview as well. So these are parts of the philosophy of the classical mechanics. It's deterministic and mechanical. In terms of the mechanical, think of the clock. There is pieces to the world. So there is pieces to the world. They interact with one another in well-defined way, and we can understand those interactions, right? It's deterministic. It's deterministic in that if you know the starting condition, then you know what's going to happen in the future. So you could imagine measuring the position and velocity of every particle in this room right now, and then it's just Newton's law or conservation law that will tell you exactly where they are going to be, how they are going to interact, and what they are going to do for all future times. This is a very powerful idea. If you believe in this, it motivates you try to design machinery, think about controlling and designing technology. It's a part of the worldview that Newton's helped to create this classical worldview. Newtonism also works backwards. You can deduce how things were before you measure them again because the rules are mechanical. The universe is in this classical viewpoint like a giant clock, and not only can you predict how it's going to be in the future, but also you know where it started at some earlier time. It's very useful. It's intrinsically reductionism. Yes. Is it intrinsic? Is it intrinsic? Well, maybe not. But there are elements of classical physics where you could just sort of despair and say, it's just too complicated for me to try to understand what's going on in terms of Newton's laws. Think about human consciousness. Even Isaac Newton probably would have conceded that it might be an awfully hard physical problem to understand in terms of the pushes and pulls. But still, it's built into the philosophy that maybe we can. Maybe the world is reductionism. That is to say, the complex things can be completely understood if you know the building block and the rule of the game. If you look at such a wonderful magical phenomenon, I love rainbows and I really appreciate their beauty. It inspires me at many levels, and yet I also appreciate the idea that a rainbow is a physical system made of little drops of water, and the light is moving through the rainbow in the way that's understandable. I can understand our arbitrary complex system in the principle by looking at the smaller, simpler constituents. So, and that worldview has been extraordinarily fruitful. Everything that you can think of in terms of the modern technology has probably come about because we believed that we could understand complex things. By and large, it's been very successful program. So as we move on through this course, we will be looking at, as I mentioned, some of the specific new physical discoveries. Electricity and magnetism are big deal in our world. We need to spend some time thinking about them. We will also move on to the both larger scale phenomena such as light and the smaller scale phenomena such as atoms and the way atoms move, the way they wave and oscillate. These gonna be very specific topic, but all of this is built from this synthesis. So these are going to be specific topics, but all of this is built from the synthesis, the classical physics of set of ideas, Newton's laws, conservation principles. That in the end are not really all that complicated at all. There is not a whole lot to this story. It's very tiny, unified. This is a part of the theme of the classical physics, and we'll be able to understand this broad variety of phenomena just by using the principle of classical physics. Thank you!